Hello everyone. Today we will talk about purification of colloidal solutions. Now colloidal solutions which we prepare either by disintegration means dispersion process or by condensation process are generally associated with some soluble impurities and electrolytes. Though small amount of electrolyte is essential for the stability of colloidal solution, but excess of it may cause precipitation of the colloidal solution. So we need to remove the excess of electrolyte from the colloidal solution. Now various methods can be employed for this purpose. Number one here is the dialysis. Dialysis. So what is dialysis? It is a process of removing a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. Since particles in a true solution can pass through animal membrane or parchment paper or cellophane sheet, but not the colloidal particles. So these membranes can be used for dialysis. So how we proceed? We make a bag of cellophane paper or anything of suitable membrane. Now colloidal solution is filled into it and is suspended in a vessel through which fresh water is continuously flowing. Now molecules and ions diffuse through membrane into the outer water and pure colloidal solution is left behind. Dialysis is a slow process. So to speed up the dialysis, we go for electrodialysis technique. So next is the electrodialysis. So this is a modified form of dialysis because ordinarily the process of dialysis is very slow. So it can be speed up using electric field, external electric field. Now if the dissolved substance in the impure colloidal solution is only an electrolyte, the process is then named electrodialysis. The colloidal solution is placed in a bag of cellophane paper while pure water is taken outside and electrodes are fitted in the compartment. Now the ions present in the colloidal solution will start migrating towards the oppositely charged electrodes. Now the third technique here is the ultrafiltration technique. Ultrafiltration is a process of separating the colloidal particles from the solvent and soluble solutes present in the colloidal solution by specially prepared filters which are permeable to all substances except the colloidal particles. Colloidal particles can pass through ordinary filter paper. Why? Because their pore size is quite large. But the pores of these special ultrafilter papers, they are of small size. So how to convert the ordinary paper into the ultrafilter paper? Ultrafilter paper having the small pore size. So for that what we do, we impregnate the filter paper into colloidal solution. The usual colloidal is a 4% solution of nitrocellulose in a mixture of alcohol and ether. So ultrafilter paper is prepared simply by soaking the filter paper in a colloidal solution and hardening by formaldehyde and then finally drying it. Thus by using ultrafilter paper, colloidal particles are separated from rest of the materials. But ultrafiltration is a slow process. So to speed up, pressure or suction is applied. The colloidal particles left on the ultrafilter papers are then stirred with the fresh dispersion medium to get a pure colloidal solution. Next, let's come to properties of colloidal solution. Properties. So the very first property is the colligative property. We know that colligative properties are the properties which depends on the number of solute particles, means number of moles of solute. And there are 4 colligative properties. Number 1, osmotic pressure. Number 2, lowering in vapor pressure. Number 3, depression in freezing point. And number 4, elevation in boiling point. Now, colloidal particles being bigger aggregates, the number of particles in the colloidal solution is comparatively small as compared to a true solution. So, in case of colloidal, the value of I decreases. Hence, the value of colligative property decreases because Van 't Hoff factor I is inversely proportional to mass, and mass of colloidal particle is larger. Next property is Tyndall effect. So what is Tyndall effect? The scattering of light by the colloidal solution. As a result, the path of the light gets illuminated is called Tyndall effect. This effect was first of all observed by Faraday, but in detail it was studied by Tyndall. Tyndall effect is due to the fact that colloidal particles scatter light in all directions in space. The scattering of light illuminates the path of beam in the colloidal dispersion. But there are two important conditions to observe the Tyndall effect. And these two conditions are, number one, the diameter of the dispersed particles is not much smaller than the wavelength of the light used. Means they should be comparable. Number two, the refractive indices of the dispersed phase and dispersion medium should differ largely. There should be large difference in their refractive indices. Now next is color. Color of colloidal solution. Now it depends on the wavelength of the light scattered by the dispersed particles. Wavelength of the light further depends on size and nature of the particles. Next is Brownian movement. In 1828, Brown observed that pollen grains suspended in water execute zigzag motion. He named this motion as Brownian movement. Later on, it was found that all colloidal solutions execute a zigzag motion. This zigzag motion is called the Brownian motion. This motion is independent of the nature of the colloid but depends on the size of the particles and viscosity of the solution. Smaller the size and lesser the viscosity, faster is the Brownian motion. Now, Brownian motion can be explained due to the unbalanced bombardment of the particles by the molecules of the dispersion medium. So this is the cause of Brownian movement, that is unbalanced bombardment of the particles by the molecules of the dispersion medium. So this is Brownian movement. Zigzag motion. Now next is charge on colloidal particles. Charge. Now colloidal particles, they always carry some charge. Now it can be positive or it can be negative. Now charge on the sole particle is due to one or the other reasons, which is due to electron capture by sole particles during electrodispersion of metals, due to preferential adsorption of ions from solutions, or due to formulation of electrical double layer. Let's talk about the preferential adsorption of ions, which is the most accepted reason. The sole particles acquire positive or negative charge by preferential adsorption of positive or negative ions. When two or more ions are present in the dispersion medium, preferential adsorption of the ion common to the colloidal particle takes place. For example, if silver nitrate solution is added to an aqueous solution of potassium iodide, silver iodide will be adsorb negative iodide ions from the dispersion medium to give a negatively charged sole. However, if silver iodide is formed by adding potassium iodide to silver nitrate solution, the sole will be positively charged due to adsorption of silver ions present in the dispersion medium. Now see, sometimes we find it difficult to understand how the same sole can be positive or can be negative. It all depends on the dispersion medium. If the dispersion medium here is the, let's say, if I have taken silver nitrate and I am going to add it to the potassium iodide. So potassium iodide is the dispersion medium. Definitely I will get silver iodide sol. Since in the potassium iodide is a dispersion medium, so iodide ions are common, so silver iodide will be absorbing iodide ions. However, if I do the reverse, means if I take silver nitrate solution as a dispersion medium and to this I add the potassium iodide, I will be getting the silver iodide, but silver iodide will be absorbing silver ions from dispersion medium, leading to a positive sol. Now the next is, what is zeta potential or electrokinetic potential and how the charge develops. The second important explanation for the development of the or for the origin of the charge. Now see, the combination of the two layers of opposite charges around the colloidal particle is called Helmholtz electrical double layer. According to modern view, the first layer of ion is firmly held and is termed fixed layer, while the second layer is mobile, which is termed diffused layer. Separation of charge is a seat of potential. So the charges of opposite signs on the fixed and the diffuse parts of the double layer result in a difference in a potential between these layers. This potential difference between the fixed layer and the diffuse layer of opposite charges is called electrokinetic potential or zeta potential. Zeta potential. We have already seen that the surface of the colloidal particles acquire either positive or negative charge by selective adsorption of ions carrying positive or negative charge respectively. It is surrounded by another layer carrying opposite charge as compared to charge on the dispersed phase particles. For example, if I said silver iodide sol is obtained and it has adsorbed iodide ions. So definitely it has adsorbed iodide ions from the dispersion medium, which is potassium iodide. So iodide ions will be forming a fixed layer, whereas the potassium ions will be forming the diffused layer or the mobile layer. Now there will be difference in the potential of these two layers. That difference is called electrokinetic or zeta potential. And these two layers, the fixed and the mobile layer, this electrical double layer is called Helmholtz double layer. Let us now proceed to the electrophoresis. So what is electrophoresis? When electric potential is applied across two platinum electrodes dipping in a colloidal solution, the colloidal particles move towards one or the other electrode. Movement of colloidal particles under an applied electric potential is called electrophoresis. Positively charged particles move towards cathode, while negatively charged particles move towards anode. When electrophoresis, that is movement of particles, is prevented by some suitable means, it is observed that the dispersion medium begins to move in an electric field. This phenomenon of movement of the dispersion medium in the presence of electric field is called electroosmosis.